This is problem 7-82 on page 363. Draw the shear and moment diagrams for the beam. Pretty simple problem statement. The beam is fairly straightforward as well. It's cantilevered. So there's a pivot on one side, a roller in the center actually, with a uniform distributed load initially for the first length of the beam, L. For the second length of the beam, which is the same length, the load linearly decreases out toward the end. They've given us a magnitude W naught of the distributed load, but no numbers to work with. We have to work this symbolically. So let's begin with a free body diagram. In fact, why redraw it? Let's just locate a force. I'll just call it A at A. Actually, it's here, so point B is here, so I'll just call it force B at this point. And then simply sum moments about point A, for example, to find reaction B. So if we sum moments about A, then the force at A will not be present. But we've got a distributed load which will give rise to a resultant which will act at the center of that length. So I'm going to quantify that load in terms of the symbols given. Now, notice that load will cause a negative moment, thus this negative sign. But the magnitude would be W naught times L, right? Because W naught times L, well, W naught is the magnitude of this distributed load in force per length. So I'll have to multiply that by length to get the total resultant load. But then I need the moment of that load, so it acts at L over 2. So there's the moment of that resultant force from the first distributed load. The second one, the second distributed load, will have a resultant. Well, I guess I could go ahead and add B and couldn't I? So let's go ahead and add this one first. So B will cause a positive moment. Its moment arm is L. That's pretty easy. What about the distributed load? Back to that. Well, the decreasing distributed load will act at a length of 1/3 of L from B. So in other words, L plus 1/3, so 4/3 L. And we'll have a negative moment, right? What about the magnitude of that resultant? Well, the magnitude would be W naught L divided by 2. Because understand, we can think of this as a rectangle, calculate its area, W naught L, and this sits as a triangle just divided by 2. So there's the magnitude of the resultant. So this sum should come out to 0 if we hope, or if we observe that this beam is static in static equilibrium. Anyway, so rearranging this equation, we can cancel a few things. You notice we have L in each term, so why don't we just go ahead and get rid of one of those L's to begin. And then we can calculate B by simply moving everything to the other side. So, for example, we have what? 4/3 W naught L from this term, well, 4/6. And then we have a further, let's do it this way, 1/2 W naught L from this term. Understand I flipped the signs because I moved them to the other side. So let's see, 1/2 is the same thing as 3/6. So this is, of course, 7/6 W naught L. There's the magnitude of the reaction B. Let me jot it down here so we'll have it. And then the last thing to do is to calculate the reaction at A. For that, we'll simply sum forces in the vertical direction, the y direction. We always think of the coordinate system being the usual. So the sum of forces in the y direction is A plus B minus W naught L. That represents the resultant of the uniform distributed load, minus W naught L over 2, the resultant of the triangular distribution. And so, rearranging for A would be equal to, let's see, negative B, but B is 7/6 W naught L, so that takes care of B. We pulled it to the other side. By the way, this sums to 0. And then pulling these two to the other side, well, 1 plus a half is 1 1/2, so that's 3 halves. So plus 3 halves W naught L. Well, we can simplify this just a bit after all, because 3 halves is what, 9/6? 3 halves, yeah, times 3, 9/6, yeah. So, 7/6 minus 9/6 is 2/6, or 1/3 W naught L. So now we've got the magnitude of both the reactions A and B, and that was the whole point of all we've done so far. So now that we've got the reactions, we'd like to create shear and moment diagrams for the beam. So let me draw the shear diagram here. I'm going to need some space. I'm going to make it large. But I will try to align it with the beam that's above. Where do we begin? Well, the shear, if you think about a little beam segment where there's hardly any distributed load because we just don't have much length, the shear, notice, would be equal to A. So that means we need to begin about here at W naught L over 3. Now, the shear decreases linearly at a rate of W naught, right? So how much length do we have to accomplish before the shear goes to 0? Well, 1/3 of the length, you see that? Once we get to length over 3, the amount we take away, so if we have a distributed load at L over 3, if we take that particular point, then, well, let's see, that L over 3 length will give rise to a resultant whose magnitude is simply W naught L over 3. But that's the magnitude of A, and so these two will cancel, and we won't need any shear at that point. So at length divided by 3, so length is from here to here, so cut it into thirds. Right there, the shear goes to 0 at L over 3. Now my drawing's not very good. There we go. If we continue to add more and more distributed load, if we get 2/3 more of the length, then that will be a further W naught 2/3 L, right? So in other words, as we go all the way to this point where B is at, I'm trying to make this a straight line, we should, let's see, let me try a little better. Here we go. We should end up at negative 2/3 W naught L. Right? Because think about it, we get to 0 here, but we just keep going, keep adding more and more uniform load. And so the 2/3 length times W naught tells us how much load we've added. Well, it's 2/3 W naught L. So that's where we end up, right before point B. Now at point B, we've got a very large reactionary load that needs to move us from negative 2/3 up by 7/3. Now 7/3 I'm sorry, 7/6. 7/6 are of course 1 plus a sixth, right? So take 2/3 out of this one, what are we left with? We'll be left with 1/3, so we need 1/3 plus a sixth. That's how high up the shear will be, right? So 1/3 plus a sixth, well this is 2/6. And so we'd have 3/6 or a half. So we end up at 1/2. Now 1/2 is above 1/3. It's more than 1/3, and so it should be roughly there. So W naught L over 2 is where we end up because of this reactionary load. So there's an increase in the shear at that point. Now, since the distribution here is, the load distribution is linear but decreasing, I expect to get a quickly decreasing curved line for my shear. Why? because really all that this shear does is integrate the load. That's all it really does. And you notice that we add more load early on than we add later. And so I expect the change, the amount of change at this end to be small, but the amount of change per length here fairly large. And so that's the shape I expect. But exactly what would that look like? In other words, if I wanted to calculate the change in shear, what would I have to do? Well, I would have to integrate the negative of the distributed load over the distance. Now, what am I integrating from and to? Well, I'm going to integrate from an x position of L. Well, I brought my axes over so far, but anyway. From L all the way up to some particular point, x. That's where I need to integrate from and to. Okay. Now, what does the distributed load look like in that section? In other words, what's the equation of the distributed load here? Well, it's negative W naught over L times X plus 2 W naught. What the heck? How did I come up with that? Well, let me show you. First of all, the distributed load is a negative distributed load because it's pointing downward. But all I really tried to do is get the equation of the line, and I noticed that the y-intercept occurs at 2 W naught, okay? So W naught is here, we extrapolate back, it would be at a height of 2 times W naught. So that was my intercept, and I noticed that the slope of this line is simply W naught over L, right? Because think about it. If you plug in an x value of L, so right here, we would get simply minus W naught plus 2 W naught. We'd have a W naught, a single W naught. That makes sense. That's the magnitude of the distributed load. If we plug in x equal 2L, well, the L's cancel and we have negative 2 omega, W naught plus 2 omega, or 2, sorry, W naught. It's not omega, it's W. And so we end up with 0 at the end. So that matches. That gives me the equation of that line. So all I have to do, this negative sign comes out from the integral. This is just part of the equation. But this negative sign is part of the fact that W, as a function of position x, is the function that we are integrating. So, excuse me, like I said, this negative sign comes out. We'll just plug in the equation. Negative W naught x over L plus 2W naught dx, integrating from L to x, where x is going to be larger than L, right? Because obviously this equation doesn't match if we're less than L. So this should give me an equation. In other words, this should give me, in functional form, an equation that tells me the change in the shear as a function of x. Okay? Give myself some space here so it's clear what I'm doing. Now this is important, that this only gives me the change in the shear. So let's perform the integration. It's pretty easy. These are just constants times x and then a constant. That's very easy to integrate. And so let's not forget our negative sign. We get plus for the first time, or for the first term, W naught over L x squared over 2. And then when we integrate this constant, we get minus 2 W naught x. And this whole thing has to be evaluated from L to x. Okay? Of course, what that means is we evaluate both terms from x to L. So we plug in the upper limit, that's easy. You get W naught over 2L x squared minus 2W naught x. It's supposed to be an x. And then we plug in the lower limit, so we have to subtract L plugged in here. So W naught over 2L L squared. So we plugged it in for x, put the 2 in the denominator to get it out of the way, minus 2W naught L. Okay? Now we notice that this factor, W naught over 2, let's see, how did I put them together initially and then I broke them back apart. What I really was trying to do is just put the squared terms together. So let's just do that. W naught over 2L x squared minus W naught over 2L L squared. But I don't really need that, right? How about if I go ahead and cancel one of the L's? There we go. So now I've taken care of both those terms. Observe the sign. And then minus 2W naught X from here. And then negative negative is positive, so 2W naught L. Okay. So then I can combine these two terms. We basically have 2 minus a half, right? Because both are multiplied by W naught L. And so the result of that is, of course, 3 halves. So I'm running out of board space here, that's what I'm struggling with. W naught over 2L X squared minus 2W naught X plus 3 halves W naught L gives me an equation for the change in the shear. Be very careful. This is the change in shear as a function of position. Change from what? Change from where it started. It started here. So if I want, what will really be useful is to get the actual shear as a function of x. Well, that is equal to the initial shear, or the shear at, I don't want to say this point back here, but at this point, the initial shear, plus the change in the shear as a function of x. Okay, well, what is the initial shear? Well, it's W naught L over 2. So, W naught L over 2, and then plus the rest of this stuff. So plus W naught over 2L X squared, I guess I'll copy it from here, minus 2 W naught X plus 3 halves W naught L. So now you notice we have 1 half plus 3 halves. So guess where we are? Well, we're back to 2 W naught L. Okay. So this is the shear as a function of position. Let's check and see if it works. For example, let's plug in x equal to L. We should get W naught L over 2. So if we plug in L here, what do we get? Well, W naught over 2, one of the L's will cancel, we'll have that, minus 2 W naught L, because we're plugging in x equals L, plus 2 W naught L, these two cancel, and sure enough, we have W naught L over 2. Well, that worked nicely. Let's double check x equal to 2L. If x is 2L, W naught over 2L, 2L quantity squared, minus 2 W naught 2L plus 2 W naught L. Now let's see, 2 2's are 4, 2 squared is 4, 4 over 2 is 2, okay. L cancels with one of the L's, and what have we got? Well, let's see, we've got W naught 2L, 2 W naught L, minus 4 W naught L. Sure enough, yes, they all cancel, okay. So we get a shear of 0. So in fact, this equation right here tells us the magnitude of the shear as a function of x from x equal to L to x equal to L. That's the range over which this equation is valid between L and 2L. Well, now that we've got that, it'd be nice to get the moment diagram. Now, all of that was a lot of work, but what we really need is just this bit of it. So let's just say V of x is W naught over 2L x squared minus 2 W naught x plus 2 W naught L. That way we've got our shear equation as a function of position. So now let's go ahead and tackle the moment part of this problem. Notice there's no moment at the beginning, no moment at the end, and so we expect to have no moment at the beginning and end. We expect our moment diagram to begin and end at 0. Now let's see if we can plan ahead just a little bit. I'm going to make this one a little bit wider because I want to make sure I've got enough room to draw. So there's L and 2L. we know that we have to begin, and hopefully we will end at a moment of 0. But let's check along the way, because the way that the moment graph changes is by integration of the shear graph. Mathematically, the change in the moment is equal to the integral of the shear as a function of position over that range, right? So we can apply this to whatever point we'd like. I think what I will do, since it's fairly straightforward, I'm not going to concern myself with these parts very much. I'll just use the fact that the area can be calculated easily and therefore represents the change in the moment. So, for example, remember this point is L over 3. I think I covered it over with my crosshatch. If I want to know how much area this is, all I need to do is take W naught L over 3 times L over 3 and divide it by 2. Now let's see, that means W naught L squared over 9 divided by 2 would be divided by 18. So that area here, instead of going through the integration, since it's a fairly simple shape, I can simply say it's W naught L squared over 18. Because it's L over 3 times W naught L over 3, and then divided by 2. So that's the magnitude of the moment once we've reached L over 3. So let me put a point up here. And this point is at, as I said, W naught L squared over 18. Now the only reason I can write that down directly is because we know that the initial moment is 0. So the change in the moment, being represented by this area, will simply give me the magnitude of the moment at L over 3. Now notice that more area is added at the beginning. If you actually looked at the functional form of this moment, which we could perform the integration, but I don't really want to do that. It would make the video too long. If we perform the integration, what we'd find is that this is a second order curve. In other words, it's got an x squared term in it. Okay? So I'll leave that to you as an exercise if you wish to figure out what exactly the equation is. But all you really have to do is figure out the equation of the shear in this section, which is easy, it's just a straight line. Take that line and integrate it with this equation, and you'll come up with the equation for that line. Now, since we're adding more and more negative area over here, well, that's going to decrease the moment. Notice I made this a peak, right? Because I know that the slope of the moment graph is the shear at this point, and the shear magnitude is 0. Therefore, the slope at this point is 0. In other words, there's a horizontal tangent line there. Okay? So as we add more and more area, there's a negative area, well, by the time we get to 2L over 3, in other words right here, we'll be back to 0, right? Because notice this is a similar triangle, right? If we take half of this larger triangle, this will have the same area as the other one. But that's not really what I want to do. I want to add all of this up and figure out how far down I'll have to go. So, well, let's see. How can we do that? Well, this area is going to simply be the base, 2/3 L, that's the base length, times the height, negative 2/3 W naught L. Yeah, let's see. So that's easy. That's, let's not forget this is a triangle, not a rectangle. So divide by 2. So 4 over, well, this is 9, 2's in the denominator, so it's 4/18, right? And of course, let's not forget the negative sign. W naught L squared. Okay. So that's how far down the moment graph needs to move. That this area represents how far down the moment has to move from this point. Because notice I started from L over 3, right? And calculating the area. So by the time we get to L, we should have moved down by 4/18. Well, here's 1/18, so we've got 3/18 to go. If that's an 1/18, and that is roughly Looks like we just barely made it. And we'll end up right there. So this should be a parabola. It just goes down to there. Passes through 0 at 2/3 L. Okay. Now, we could use something similar to calculate this, but this curve is a little more complicated. It's a second order curve. So I think I'll simply integrate it in order to illustrate how this would be done. So I'd like to integrate from L. I only want to concern myself with this curved section of the shear. I'd like to integrate from L up to some point X again. Okay? So from L to X. Well, and fortunately we have an expression for the shear as a function of X position, so let's just plug it in. W naught X squared over 2L minus 2 W naught X plus 2 W naught L dx. Integrating the form of x to the n dx is really straightforward. The integral of x to the n dx, all you have to do to remember this is add 1 to the exponent and divide by that exponent. That's all you've got to do. So the constants just come along for the ride. W naught over 2L. X squared will become x cubed by 3. Again, for the next term, constants come along for the ride. Negative 2 omega naught, or W naught, times x squared over 2. Finally, plus 2 W naught L x. Now this has to be evaluated from L to X. Now I'm running out of space, and I don't want to erase my diagram or any of this work yet, so let me cheat just a bit. And I have to get rid of this for the time being. And we'll go up here and continue our work, okay? So plugging in X, well, all we got to do is copy what we've got. W naught X cubed over 6L, put in the 2 with the 3, minus, let's cancel these two 2's, W naught X squared, trying to save some space, plus 2 W naught L x. And then we've got to subtract off the lower limit, so minus W naught L cubed over 6L. Of course, these L's, one of them will cancel, and we'll just have L squared. Minus W naught L squared plus 2 W naught L times L. Because, of course, I've evaluated X as L here. So L is the same thing as L squared. So if we just subtract off one of those, we end up with simply 1 W naught L squared term left. Okay. And so this expression should tell us how much the moment changes in moving from here on to 2L. So let me simplify it just a bit further. Let's see, we've got an x cubed term. Actually, I may not be able to simplify it further. Let me look at it. Yeah, we can get that negative sign in there. So W naught x cubed over 6L, that takes care of the cube term. There's a square term, minus W naught x squared. There's a first order term, plus 2 W naught L x. And then, let's see, actually we can combine these two, right? Because W naught L squared are the same factor. So this is 1/6 plus 1, so minus 7/6 W naught L squared. Because of course that negative sign makes both of those negative. All right, so this should tell us how much the moment changes. Now, it's not particularly difficult to draw this. It's going to be a curve something like this, because again, we're changing the moment more. That's what this area represents. We're changing the moment more early on than we are later on. There's less area at the end, so the moment changes more gradually here, versus large changes on the moment axis here, small changes on the moment axis here for the same change in position along the length of the beam. And of course the equation of this line, well, it's almost right there, except this is the change in the moment. If you actually want the moment itself, to get the magnitude of the moment, you'd have to take the initial moment plus the change in the moment. So if I actually want to write down the equation of this line as a function of x, what I need to do is add the initial moment, which I thought I had written it down, but I guess I've either erased it or I don't know what I've done with it. We came down by 4/18 W naught over L, so the magnitude of the moment at this point is simply negative 3/18 W naught L squared. And that is a negative sign. Okay? Because we moved from here all the way down by 4/18. That's why I made, all these quarter, or well, 18th tick marks. Okay, so what we need to do then is add this, which is the initial moment, to the equation for the moment. Let me do it over here so it'll be a little cleaner. So minus 3/18 W naught L squared. Let's see, where will we end up putting that? We'll put it with this term, so minus 7/6 W naught L squared, and then the rest of this stuff that actually involves x. Let me combine these two first. For example, if we take 3 times 7 is 21, 3 times the 6 we had would be 18, that way we have a common denominator. And both of these are negative, so we end up with 3 and 21 are 24. Combining the two terms together. And now we simplify, 12/9, divide both by 3, 4/3. Okay. So that's the constant term, and all we need then are the terms that depend on x. We need some space, I guess, as well. Where were we? So we've got that term, we already took care of that. We took care of the initial moment. So now we're just writing down the change in the moment, and we were at the squared term, now we got that. So we're at the first order term, and we're almost done. W naught Lx. There we go. Now here's my question. Do we actually end up at 0? In other words, when I plug in for x, when I plug in 2L, will I get 0 out of this monster? I've gone away from my worksheet enough. I guess I may as well go ahead and just continue working this at the board. Let's make our lives easy, first of all. Let's factor out this. Do I want to do that? Yeah, I guess I'll leave it alone. Let's just plug in 2L. So minus 4/3 W naught L squared. And from this term, plus W naught, and we need 2L cubed by 6L. This term, minus W naught 2L quantity squared. Finally, the last term, plus 2 W naught L 2L. All right, so let's see. If we put these two L's together, we'd have L squared. Put the 2's together, we have 4. Simplify this just a bit, we'd have 4L squared, because 2 times 2 is 4. We notice immediately that W naught L squared plus 4 minus 4, those two cancel and are gone. So that's nice. Now do these two cancel? Well, let's find out. 2 to the third power is 8. We'd have L cubed remaining. Cancel one of the lengths, L squared. And 8/6 are the same thing as 4/3. And sure enough, negative 4/3 W naught L squared plus 4/3 W naught L squared. And yes, this all comes out to 0. So when we evaluate at x equal to 2L, sure enough, we got 0. And so now I could finish writing down the equation here. I guess I'll just copy it. W naught x cubed divided by 6L minus W, you know what, let me factor out the W naught. Maybe that'll save me some space. So where were we? W naught x cubed by 6L. W naught's out, x squared. W naught's out plus 2LX. And then finally, the constant term, W naught out, minus 4L squared over 3. So there's the moment as a function of position along the length of the beam from L to 2L. Understand, this moment equation has nothing to do with this, right? It doesn't tell us what the moment is as a function of position between x equals 0 and x equal L. It only tells us the moment as a function of position between x equal L and x equal to 2L. Of course, that's supposed to be a 4. It may not look like it on the video. So we've got a third order term, second order, first order term. This is not a parabola, but it kind of looks like it. It's a curved line. And I think we've answered all of the questions they had. They wanted the shear moment diagram. And notice we performed all of these computations symbolically.